Numeric integration is used when you have a function that does not have a simple antiderivative. I'm going to try to type some of this just to make this a little bit quicker and easier to see on all of you, but some functions have no simple antiderivative. And when I say simple, I mean nothing that we can compute with standard means or even some non-standard ones. So, for instance, if I have f of x equals the cubed root of x times the square root of 1 minus x, that's an example of a function that won't work. Another one, just throw some of these down here, that has been given as not working is if I have radical x times the cosine of x. We don't have a way to find a standard derivative of that. And you can try to do all the integration by parts you want. You're not going to end up working with that. Another weird one that does not work is the cosine of x. Let's make sure I have the right parentheses over x. I'm running out of letters. Let's use a capital F. That's not the right F. Here we go. Another one is radical 1 minus x cubed. And here, I'll give you another example. This is another one that you think would work, but we really don't have a way to find one for it. The sine of x squared. So all of these are examples of functions that just will not give us some clean derivatives, or clean integrals. So if I want to find an integral, we have to go back to a system that we used a while ago, the trapezoidal rule. The trapezoidal rule, to review, and I would want you to review your trapezoidal rule, is we state the integral from a to b of f of x dx could be approximately 1/2 the average of b1, or the average of b minus a, so I'm not saying that right, 1/2 b minus a over n, and b minus a actually splits a whole region up into this whole part, and n is the number of subintervals. So basically, it's the constant width. So this is 1/2 the width of all these, then times the height of successive trapezoids, which you can average as or simplify to f of x sub 0, and x sub 0 is just equal to a, plus 2 f of x sub 1, and this would be x sub 1 here, plus 2 f of x sub 2, and all the way to 2 f of x sub n minus 1. This would be x sub n minus 1, and finally b would be equal to x sub n, f of x sub n. So that's trapezoidal rule. We did it as the average of LRAM and RRAM, but really this is trapezoidal rule by itself. Remember that what you're actually doing is you're saying f of x sub 0 plus f of x sub 1, that's one group, and then f of x sub 1 plus f of x sub 2. And the over 2 part is to average those two, that would distribute, and it basically creates an average of all of them. So this is the area of a trapezoid just repeated ad infinitum, and it creates this effect of having an infinite number of trapezoids. They all have the same base, but you're actually just modeling this equation off of what is a lot of small lines. One thing to keep in mind is that as n goes to infinity, the integral gets, use the word better. The approximation gets closer to the actual. And if you want it to truly be the actual, you could do a limit as n approaches infinity. So that's trapezoidal rule. We found that before, trapezoidal rule or MRAM were best, but I want to hit up that trapezoidal ultimately takes a curve and models the curve by creating lots of linear segments and then finding the area under those segments and adding them all up. And that's essentially trapezoidal. These are what I would call curve is approximated by first degree polynomials. And first degree polynomials are really just what we call linear polynomials. It's approximated by a linear curve. Okay. We're going to learn a lot more about approximating curves in the next chapter in the regular course of calculus, the infamous chapter 9. I know you're sick of hearing me hype it up for all this time. But I want to introduce a second way to do this approximation, and this is called Simpson's rule. And to be honest, I had never really encountered this before deciding to do this. But when I made these notes the other day, this was actually really interesting. It's a second-degree polynomial model. And instead of modeling off of all these off of linear pieces, you're going to model them off of quadratics. This is a little bit tricky to kind of generate, so don't worry so much about memorizing this derivation, but just appreciate where it comes from. Any polynomial p of x that's second degree can be modeled off of ax squared plus bx plus c. And so the integral from a to b of all these little polynomial pieces would be ax cubed over 3 plus bx squared over 2 plus cx evaluated from a to b, which means that if you substitute that a and b in, you're going to get a b cubed minus a cubed over 3 plus b squared minus a squared over 2 plus c b minus a. I would expect you all to be able to factor out from all three of these a b minus a. If I factor the b minus a out of the first one, well, let's also factor out a b minus a, and I'm going to factor out a b minus a over 6, which has the effect of multiplying by a 6 inside. That's going to give me a 2a. Factoring a b minus a out of the difference of cubes gives me b squared plus ab plus a squared. Factoring it out of the difference of squares and multiplying by 6 gives me a 3b b plus a. And then finally, this gives us 6c if I multiply by a 6 and factor the b minus a out. So you get this. And the next step I'm not going to go through in detail. Your book does this, but it doesn't actually do it in detail. It just kind of says we collect terms and manipulate to get to this step, which you can prove by multiplying out that it's equivalent to the previous step. It's not so important how you get to this step, just more that you can easily show that this step and the previous step are the same. You get aa squared plus ba plus c plus 4 times a times b plus a over 2 squared plus b times b plus a over 2 plus c plus, then in a third set of parentheses, a b squared plus b plus c. I just want you to see the three pieces here, this, and this, which means I'm missing a closed parentheses here. Okay, again, don't worry about how you got from the previous step to that step. Just know that if you had to in a crunch multiply it all out, you could easily prove that they are the same thing. What is important about this last step is what you really end up with. This aa squared plus ba plus c is p of a. It's just the polynomial with a plugged in. This middle one is 4 times p of a plus b over 2. It's the polynomial when you plug a plus b over 2 in. And then the last one is the polynomial when you plug b in, p of b. I'm going to keep the highlights consistent. Well, so knowing that those three are consistent means you actually now have what this integral ends up becoming. This is the area of this. It's the integral of a polynomial, just kind of simplified. If you take a region and you partition it, which just means to split it up into n subintervals, and for reasons that we'll explain here, n has to be even. This has to do with the fact that you're going to be pairing all these up. N has to be even. We can say that a, which is equal to x sub 0, so we could create these x sub 0, x sub 1, x sub 2, x sub 3, all the way up to, I want to have even, so let's go x sub 4, all the way up to x sub n minus 2, x sub n minus 1, and x sub n. And x sub n is just the same thing as b. So I'm breaking this up into small intervals. These are all evenly spaced, just like they were before. What I'm basically doing is I'm going to pair these three and say that this is the region from x sub 0 to x sub 2. This is going to be one 3-point thing. Then this is the region from x sub 2 to x sub 4. And then this is the region here from x sub n minus 2 to x sub n. And you might be wondering why that's important that we have these three. That was curious to me too until I realized you need 3 points to make a unique quadratic. So it took 2 points to make a unique line, which is why the trapezoid was based on 2 points. Now we need 3 points. So if I take the same interval here, I'm actually going to say, okay, so these three are one quadratic, these are another, these are another. Everything gets kind of made into these pairs of regions. These intervals are now going to be paired up. So that's why we do that. It takes 3 points to make a unique quadratic. So in a way, this quadratic here is the quadratic of the one that passes through x sub 0, y sub 0, x sub 1, y sub 1, and x sub 2, y sub 2. And then rinse and repeat. This is going to go through x sub 2, y sub 2, x sub 3, y sub 3, x sub 4, y sub 4, and so on and so forth. So that is just an example of why we need it done like that. Now, if I were to take this polynomial right here and integrate from x sub 0 to x sub 2 of f of x dx, that's going to be approximately, remember using the polynomial to model it, that's going to be about the same as the integral from 0 to x squared of p of x dx. Remember, f is the curve, but p of x is the polynomial model we're creating with those 3 points. So this is now equal to, by my formula up above, b minus a, so x sub 2 minus x sub 0 over 2, over 6, times p of x sub 0 plus 4 p of the average of x sub 0 and x sub 2 plus p of x sub 2. So that is the gist behind this. And if I kind of simplify a few things and just replace a few things, this x sub 0 minus x sub 2, or x sub 2 minus x sub 0 is actually equal to 2 intervals. It's 2 b minus a over n's. Remember, this is just the difference between 2 regions. So that's actually the width of 2 subintervals. So this is the same as saying 2 subintervals. Still have the over 6. And this p of x sub 0 is the same. The average of x sub 0 and x sub 1 is, or x sub 2 is just x sub 1. This should use a different color. This x sub 0 plus x sub 2 is the same as x sub 1, or x sub 1. And then finally that p of x sub 2. And you end up with canceling the 2 and the 6 to get b minus a over n p of x sub 0 plus 4 p of x sub 1 plus p of x sub 2. This is the area under just those 3 points, x sub 0, x sub 1, and x sub 2. So if I model that with a polynomial and I try to do an area, I now have the area of that with this formula here. If I add up an infinite number of these, or not an infinite, a finite number from region to region, that is called Simpson's rule. And what Simpson's rule says is, first, let f be continuous on a to b, and let n be an even integer. The integral from a to b of f of x dx is approximately b minus a over 3n. Oh, I forgot the 3 right here. You probably noticed that, but I caught it. b minus a over 3n times f of x sub 0 plus 4 f of x sub 1 plus, now it would be f of x sub 2, but we're going to add that to the next triple set. So that's going to be 2 f of x sub 2, then 4 of f of x sub 3, then 2 of the next one, and they keep adding in that order until you get to the very end, where you then have 2f of x sub n minus 2's, 4f of x sub n minus 1's, and then that final f of x sub n, all at the end. In essence, whereas the trapezoidal rule went in a 1, 2, 2, 2, 2, 1 pattern, the coefficients of this go in a 1, 4, 2, 4, 2, 4, 2, etc., until you end with a 2, 4, and then 1. So that's the pattern of coefficients that happens here. Also, like before, as n approaches infinity, the approximation is better. But this is already a better approximation than trapezoidal rule. So the next bit is to try this. We're going to try this on 0 to pi of sine of x dx. And we're going to try this in a couple of ways. We're going to do trapezoidal, or we're going to do n equals 4. So the trapezoidal rule for n equals 4 is to do 1/2 b minus a over 4, because over n. Then I do the sine of 0 plus 2 times the sine of, we're breaking it up into fourths, so sine of pi over 4 plus 2 times the sine of pi over 2 plus 2 times the sine of 3 pi over 4 plus the sine of pi. Now, simplifying this, I get pi over 8 times sine of 0 is 0, sine of pi is 0, sine of 2 times that is root 2, plus the other root 2, because these are going to be the same thing. You get 2 root 2, and plus the remaining 2. Simplify, and you get pi over 4 root 2 plus 1. And that's going to approximate to about 1.896. Now we're going to do trapezoidal with n is equal to 8. So this is going to be pi minus 0 over 8. Doing this out, we need to split this up into 8ths. Sine of 0 plus 2 sine of pi over 8 plus 2 sine of pi over 4 plus 2 sine of pi over 2 plus 2 sine of 3 pi, I forgot the 5 pi or 3 pi over 8, my bad, plus the sine, 2 times the sine of 3 pi over 8 plus 2 times the sine of pi over 2 plus 2 sine of 5 pi over 8 plus 2 sine of 3 pi over 4 plus 2 times the sine of 7 pi over 8, and finally plus the sine of pi. I won't go through this too much in detail, except to say, well, I'll go a little bit. Those cancel for the same reason. You really should be aware that this value and this value are the same, as well as this value and this value, because of how sine works in the quadrants. This is going to simplify to pi over 16, and you're going to end up with 4 times the sine of pi over 8, because again, those two are the same. You're going to end up with 2 root 2. You're going to end up with 4 sine of 3 pi over 8 plus 2. Or if you simplify this just a little bit and cut a 2 out, 2 sine of pi over 8 plus root 2 plus 2 sine of 3 pi over 8 plus 1. And I guess I do that just because I'm frustrated that we are going to have to put this into a calculator and get about 1.974. So that is trapezoidal with n equals 8. Now let's go to Simpson's rule. And we're going to do Simpson's rule with n equals 4. Simpson's rule starts with b minus a, so pi minus 0, over 3 times n, so over 3 times 4. Then you do the sine of 0, 4 times the sine of the next one, so that's 4 times the sine of pi over 4. Then 2 times the sine of pi over 2. Then 4 times the sine of 3 pi over 4. And then 1 times the sine of pi. This is going to get a pi over 12. Those go away. And you're going to simplify to 2 root 2 plus another 2 root 2, which is going to basically simplify to pi over 6, 2 root 2 plus 1. And that approximates to about 2.005. Let's do Simpson's rule with n equals 8. Pi minus 0. 3 times 8. This is going to take longer to write than it is to calculate. But let's do this. Sine of 0 plus, remember the coefficients are 1, 4, 2, 4, 2, 4, 2. So if you know that, then you're really well on your way. Sine of pi over 8 plus 2 sine of pi over 4 plus 4 sine of 3 pi over 8 plus 2 sine of pi over 2 plus 4 sine of 5 pi over 8 plus 2 sine of 3 pi over 4 plus 4 sine of 7 pi over 8 plus the sine of pi. Phew. Okay. That gives me a pi over 24 times. The sine of 0 goes away, the sine of pi goes away. You have some that match again. Those are the same, and these are the same. So if I add them together, I get 8 sine of pi over 8 plus 8 sine of 3 pi over 8. The other ones add up to give a root 2 plus root 2 are 2 root 2, and then you also have that 2 sine of pi over 2. So you can simplify that by cutting a 2 out. I'm going to skip that right now and just go right away to 2.0003. Let's see how good these Simpsons are compared to the trapezoidals. Let's actually calculate the integral from 0 to pi of sine of x dx, which would be equal to the negative cosine of x evaluated from 0 to pi, and that is equal to 2. So you can compare and look back at our results and see we actually got a lot closer when we went with Simpson's rule. The margin of error was much smaller. This margin of error is 0.104, this is 0.26, this is 0.005, and this is 0.0003. That is really close. So I think it's a neat process. You may not value the idea of approximations, but remember, you can't do this by hand otherwise. And why do it by hand when you have a calculator? Well, that reason's coming. There's one more little bit about this, and that has to do with error. Theorem 8.6 in your book states, without a proof, and I don't feel the need to offer one or find one right now, that if f has a continuous second derivative on the interval a to b, then the error e in the integral from a to b of f of x dx on the trapezoidal rule is less than or equal to b minus a cubed over 12n squared times the maximum value possible of the second derivative as evaluated between a and b. I'm going to hold on that and explain that more in a bit, because that's your first exposure to something like this. But if you sit with this, it will make Chapter 9 go a ton easier. Let's go with the second one, because that was trapezoidal. Let's do the Simpsons version. If f has a continuous fourth derivative on a to b, then the error e in the integral from a to b of f of x dx on Simpson's rule is, it's similar, b minus a to the fifth over 180 n squared times the maximum value of the fourth derivative, and that's what that notation means, the fourth derivative of f between a and b. So keep those nearby. The question that we would ask is determine the value of n such that the trap rule of the integral from 0 to 1 of root 1 plus x squared dx has an error less than or equal to 0.01. So what you're trying to say is how many intervals do you need to get an error within that amount? There's a sweet spot. You can choose a lot of n's, but that takes a lot to calculate. You can choose few n's, but you might not get a good enough result. You want to figure out, based on the error you want, what's the best way to do this. The solution to this is to first state that f of x is equal to 1 plus x squared, then define its first derivative, which I'll leave that to you to do, and skip right on to x 1 plus x squared to the negative 1/2, and then define its second derivative, which I'll also leave to you. You can do a product rule on that, and you end up with 1 plus x squared to the negative 3/2. Okay, so we got our second derivative. Then the max value of the absolute value, oh, I forgot the absolute value part. So I should fix these two here. Those are absolute value bars. But the max value, the absolute value of f double prime of x on 0 to 1. So what's the biggest that derivative is going to be? Well, that derivative is right here, and the biggest it's going to be is if you plug 0 in, and you get f double prime of 0 is equal to 1. That's the biggest it's going to be between 0 and 1. So what that means is that this error is less than or equal to b minus a cubed over 12n squared times that absolute value of f double prime of 0, which we found was the max value. And if I simplify everything, so b is 1, a is 0, you get 1 cubed over 12n squared times 1. So this absolute value of error needs to be less than or equal to 1 over 12n squared. To make that happen, well, what do we want? We want that error has to be, this is a cap, this is a maximum on this. We want this error to be less than or equal to 1/100th. So let's take this now and figure out what that would be. If I think about the way the relationship works, this means that 12n squared has to be greater than or equal to 100. And if I solve for an n that's going to make that work, divide by 4, you get 25/3. Take a plus or minus square root, you get n has to be greater, well, it's absolute value, so it doesn't matter. N has to be greater than or equal to 5 over root 3, which is about 2.89. So n has to be greater than or equal to 2.9. We can choose n equals 3. And if you do this Simpson's, or this trapezoidal rule with three subintervals, you can get an error for this integral that's less than 0.01. Obviously, if you want a better result, choose a bigger region. So that's the gist of it, and that's all I really want you to work with on this, is just to try to be able to calculate an error, or to be able to decide what must the error be in order for this to work. Obviously, if you use Simpson's rule, it's a little bit more complicated to do the fourth derivative, but every one of these should be accomplishable, and it's not anything intended to be crazy. So that's it.